A robot has just done something that seemed impossible, and engineers around the world are paying attention. A robotics company based in Singapore has unveiled a robot capable of peeling an apple autonomously, using two hands that mimic human movements with a level of precision never seen before. It sounds simple. It isn't. Peeling a fruit requires millimetric control, sensitivity to touch, constant force adjustment, things that robots have always gotten terribly wrong. Until now. What Sharpa revealed this week calls into question everything we thought we knew about the limits of machines. In this video, you will understand how it works, why it is a turning point for robotics worldwide, and what this apple-peeling robot tells us about the future of human work. Want to understand everything? Then stay with me until the end, and I'll explain it all. But first, leave your like and subscribe to the channel. That way, you'll always be up to date on the latest news in robotics. Sharpa, a robotics company headquartered in Singapore, revealed this Monday, March 30th, 2026, a humanoid robot capable of peeling an apple in a completely autonomous manner, using dual hands that reproduce human movements with surprising dexterity. The video released by the company shows the robot executing repeated cycles of peeling and rotating the fruit, the same gesture a human would make with a knife and wrist, with no direct human intervention during the task. Why does this matter so much? Because peeling an apple is not at all simple for a machine. The task involves controlling 63 degrees of freedom, alternating between multiple motor skills, and integrating diverse sensory inputs, challenges that traditional robotics models still have enormous difficulty managing reliably. In other words, it is exactly the kind of problem that keeps engineers up at night. The system that makes this possible is called MoDE-VLA, short for Mixture of Dexterous Experts, and combines computer vision, language, touch, and force detection to execute complex movements. Instead of micromanaging each finger, the human operator provides general high-level instructions, while artificial intelligence handles all the fine coordination. The hybrid approach, human as guide, AI as executor, is what makes the system so different from anything that existed before. Sharpa is not exactly a newcomer to the sector. In recent months, Sharpa has accumulated significant international recognition. In November 2025, the company announced that its flagship product, the SharpaWave robotic hand, was awarded as a highlight at the CES 2026 Innovation Awards in the robotics category, one of the most coveted distinctions in the consumer technology sector, which received a record number of more than 3,600 entries. And it didn't stop there. In December 2025, the company announced that the SharpaWave had entered mass production, with the goal of supplying the growing market for general-purpose robots with hardware capable of achieving manipulation levels comparable to those of humans. The humanoid robotics sector is living through a historic moment of acceleration. According to the International Federation of Robotics, IFR, the global market value of industrial robot installations reached a new all-time high of $16.7 billion, and the field of humanoid robotics is expanding rapidly, with companies and researchers moving from prototypes to real-world deployments. In this context, demonstrating that a robot can perform a household task as delicate as peeling a fruit is not just a technical achievement, it is a market positioning statement. And what comes next may surprise even more than the peeled apple. To understand why this specific demonstration is a qualitative leap over everything that came before, we need to get into the details of what was built and how it works. For someone watching the video for the first time, the scene seems almost mundane. Two robotic hands hold an apple and peel it with a knife. But behind that seemingly simple movement lies an artificial intelligence architecture that represents a real leap forward from the state-of-the-art in manipulation robotics. Let's start with the hardware. The SharpaWave is a human-scale robotic hand equipped with 22 active degrees of freedom and Sharpa's proprietary dynamic tactile array (DTA) technology. Each fingertip integrates a miniature camera alongside more than 1,000 tactile pixels, capturing forces ranging from the lightest touch to heavy loads with a precision of 0.005 newtons. For reference, 0.005 newtons is equivalent to the weight of half a gram. The hand feels the difference between touching a soap bubble and squeezing an apple. The SharpaWave also features 6-dimensional force detection, ensuring dynamic grip control and slip prevention. But hardware alone would not solve the problem of peeling an apple. To overcome the main limitations of dexterity robotics, Sharpa's researchers introduced a two-component framework, the IMCopilot and the MoDE-VLA. Each has a specific and complementary function, and understanding how they fit together is the key to grasping the breakthrough. The IMCopilot, short for In-Hand Manipulation Copilot, is a set of micro-skills trained through reinforcement learning. Imagine teaching it in the same way we train animals or children, by repeating situations until the correct behavior becomes automatic. During data collection, the IMCopilot operates in shared autonomy mode. Humans control the broad arm movements while the system handles the delicate hand movements, such as rotating the apple on the correct axis. During the actual execution of the task, the IMCopilot functions as a low-level skill that can be triggered by the robot whenever fine manipulation is needed. It is as if the robot had an automatic motor instinct that kicks in at the right moments. The MoDE-VLA solves a different challenge. how to integrate very different types of sensory information without one piece of data drowning out another. Instead of treating all data uniformly, the system processes visual, force, and tactile signals through specialized pathways. Using a mixture of experts approach, it dynamically activates the relevant modules, such as contact event detection, and refines actions in real time. Think of it like an orchestra. Each instrument plays its part at the right moment, rather than everyone playing together all the time. The test results show how this architecture works in practice. The system was evaluated on 4 tasks of increasing complexity: gear assembly, charger insertion, tube reorganization, and apple peeling. The MoDE-VLA significantly outperformed the baseline models, doubling success rates in rich contact manipulation scenarios. In the most demanding test, apple peeling, the system achieved a 73% peeling completion rate, successfully executing repeated cycles of peeling and rotating. The framework also demonstrated high precision in tasks such as charger insertion, where millimeter-level accuracy is critical. For comparison, before this framework, equivalent systems achieved in the same type of task with rich physical interaction much lower success rates. Sharpa claims to have doubled the results of baseline models. What changed compared to what existed before? VLA models, vision language action systems that interpret vision and language and transform them into physical actions, were already being used for simple tasks like picking and placing objects with rigid grippers. These approaches were largely limited to simple pick-and-place actions using basic grippers. Human-like tasks, such as peeling an apple, remain difficult for robots, requiring precise coordination, force control, and constant hand adjustments. What Sharpa did was use hands with 10 articulated fingers, millimetric touch, and an AI architecture that knows when to trigger each type of control. It is a generational difference, not one of degree. The most immediate and concrete impact of this demonstration lies in 2 sectors: the food industry and the domestic market. The global food robotics market was valued at $2.76 billion in 2025 and is projected to reach nearly $15 billion by 2034, growing at an annual rate of 20.6%, driven directly by labor shortages, demand for more safely processed food, and the pursuit of greater production efficiency. A robot capable of performing delicate manipulation tasks such as peeling fruits, cutting vegetables, or assembling meals with the human dexterity demonstrated by Sharpa represents exactly the kind of advancement this market has been waiting for. For the professionals who currently perform these tasks, especially in food processing chains, which employ tens of millions of workers globally, the signal is clear. Advanced automation is coming for the functions that were previously believed to be protected from technological substitution because they required fine manual skill. But there is another side to this coin. The International Labor Organization projected that, by 2025, automation technologies, including AI and robotics, will have created at least 12 million more jobs than they eliminated. Manufacturers will need technicians capable of integrating, training, and maintaining systems like MoDE-VLA. Hospitals, hotels, factories, and homes that adopt these robots will create demand for professionals specialized in autonomy supervision and task customization. The question is not just whether there will be more or fewer jobs, but which skills will be valued in the next decade and who will be prepared for them. Sharpa's demonstration generated immediate debate in the robotics community. The central point of interest, and also of caution, is what the 73% success rate in peeling actually means. For enthusiasts, it is a remarkable result. Doubling success rates in manipulation with rich physical contact is a relevant quantitative leap, and the MoDE-VLA architecture demonstrates an intelligent way of combining distinct sensory experts. The idea of the copilot, in which an AI automatically learns the most difficult micro-movements while the human maintains overall control, is elegant and potentially scalable to other complex tasks. For the more skeptical, however, 73% is a rate still far from what would be needed for reliable commercial use. In an industrial kitchen that processes 1,000 apples per hour, failing 27% of the time is unacceptable. From a privacy and security standpoint, the sensory data captured by robots, including video, touch, and domestic environment mapping, represents an extremely sensitive asset. As robots become more integrated into workplaces, concerns grow about the data they collect, including video, audio, and sensor streams. For robots operating in domestic kitchens or hospitals, this risk is even more relevant. Now, how does Sharpa position itself against the competition? The field of dexterous robotic hand hardware is small but competitive. The SharpaWave sets itself apart by combining 22 active degrees of freedom with its dynamic tactile array technology, which integrates a miniature camera and more than 1,000 tactile pixels in each fingertip, capturing forces with a precision of 0.005 newtons. This combination of vision and granular touch at the fingertips is what the company calls seeing by feeling, a proprietary architecture that, as far as is publicly known, has no exact equivalent on the market. But the field of humanoid robots with advanced hands is expanding rapidly. Tesla, with the Optimus Gen 3, plans hands with 22 degrees of freedom per unit, the same number claimed by Sharpa for the SharpaWave. The difference lies in the focus. The Optimus is a full-body robot designed for factory tasks at massive scale, while Sharpa concentrates its innovation on the hand system and dexterity control software. And now, on the MoDE-VLA framework that orchestrates everything. Boston Dynamics' Atlas, with 56 degrees of freedom across the entire body, is currently in the testing phase in industrial pilots, with a commercial launch expected between 2026 and 2028, with price estimates ranging between $140,000 and $150,000 per unit. Where does Sharpa still fall behind? In scale. The company only just began mass production of the SharpaWave in December 2025, which puts it behind competitors such as Tesla, which had already built around 1,000 Optimus prototypes deployed internally in its factories during the same period. Sharpa has also not disclosed data on cost per unit or a deployment timeline for external customers, information that will be critical to its real competitiveness in the market. What nobody expected, however, was that a relatively young company from Singapore would be the first to present a robot with dexterous hands peeling a fruit at 73% efficiency and a published, replicable AI framework. That is exactly the kind of surprise that tends to change the direction of an entire industry. Sharpa's apple peeling robot is not just an impressive video to share on social media. It is the materialization of a problem that robotics engineers have been chasing for decades, teaching a machine to feel and act on physical objects in the real world with the same adaptability as a human hand. The MoDE-VLA framework represents a concrete technical answer to that challenge, combining cutting-edge AI architectures, advanced sensory hardware, and an intelligent division of responsibilities between human and machine. The results still have room to grow, and the challenges of scale, regulation, and cost are real. But the inflection point is clear. Dexterity Robotics has left the laboratory and is knocking on the kitchen door. And you, what do you think? If a robot with the ability to peel fruits, prepare food, and perform fine household tasks like those demonstrated by Sharpa existed, would you buy it? And which tasks would you truly trust this machine to handle? Leave your answer in the comments. If you enjoyed the video, leave your like and subscribe to the channel. That way, you will always receive notifications of new videos. Until next time.